Hi, this is Schwartz from MasterMathMentor.com. This is video AB10. Topic is differentiation of trig functions. It covers the AB manual, pages 47 through 50. Stop the video after listening to these instructions. On page 47, there's a graph of f of x equals sine of x that is also shown on the slide. On this graph, draw the tangent lines to the curve at x is equal to 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Then, from the sketch, approximate the slopes of the tangent lines, which is the derivative of sine of x, by completing the chart, and then plot those points on the graph. If you connect the dots, what trig function does the derivative of f of x suggest? When you complete the chart as shown, and then plot the points, and then connect the dots, it appears that the graph of the derivative of the sine function appears to be the cosine function. Let's do the same thing with the graph of g of x equals cosine of x. Stop the video and draw tangent lines at x is equal to 0, pi over 4, etc. to 2 pi. Complete the chart, calculating the approximation of the derivative at those points. Plot those points on the graph and then connect the dots. What function does the derivative of g of x equal cosine x suggest? The graph of the derivative of the cosine function appears to be the negative sine function. So we present, without proof, two derivatives of trig functions. The derivative with respect to x of sine of x is cosine x, and the derivative with respect to x of cosine x is negative sine of x. To take the derivative of the tangent function, we write it in the form of y equals sine x over cosine x. This is a quotient, so we square the bottom, and the numerator is the bottom, cosine x, times the derivative of the top, cosine x, minus the top, sine x, times the derivative of the bottom, negative sine of x. This becomes cosine squared x plus sine squared x, which we remember from pre-calculus is 1. So y prime is equal to 1 over cosine squared x, which is secant squared x. The derivation of the other three trig functions, y equals cosecant x, secant x, and cotangent of x, are shown. I leave it to you to stop the video and look at the actual steps to get to the final answers. In calculus, we use trig functions a great deal. You don't want to go through the derivations of their derivatives each time, so you need to memorize them. However it works for you, you must know the derivative of all 6 trig functions. The sine function, cosine function, and tangent function are used extensively in calculus. The derivative of sine of x is cosine of x, the derivative of cosine x is negative sine of x, and the derivative of tangent x is secant squared of x. The second column, the functions are not used as extensively, but still must be memorized. The derivative of cosecant x is negative cosecant x cotangent of x. The derivative of secant x is secant x tangent of x. And the derivative of cotangent of x is negative cosecant squared of x. Note that trig functions that begin with the letter c have derivatives that are negative. The derivatives of the sine and cosine functions are cyclic, which means that their derivatives form a pattern. So if f of x equals sine of x, the first derivative is cosine of x, the second derivative is negative sine of x, The third derivative is negative cosine of x, and the fourth derivative is sine of x. We're right back to where we started, and the pattern repeats. So the fifth derivative is cosine of x, the sixth derivative is negative sine of x, the seventh derivative is negative cosine of x, and the eighth derivative is sine of x. So the cycle repeats every 4. So the 50th derivative is the same as the second derivative, which is negative sine of x. The same thing is true with cosine of x. The first derivative is negative sine of x, second derivative is negative cosine of x, third derivative is sine of x, and the fourth derivative is cosine of x. And again, the pattern repeats. So if we want the 50th derivative of cosine of x, it turns out to be the same as the second derivative, which is negative cosine of x. We now have 4 basic derivative forms: power, product, quotient, and trig. And the chain rule, of course, is always in effect. The power rule is in the form of an expression to a power. The product rule is in the form of an expression 1 times expression 2. The quotient rule is in the form of expression 1 over expression 2. And the trig rule is one of the 6 trig functions of an expression. In taking derivatives, we have to be careful to identify the form. Just because there's a power in the problem doesn't mean that it's a power rule form. Just because there's a trig function in the problem doesn't mean that it's a trig function form. When writing trig functions, we will usually rewrite it adding parentheses or brackets for clarification. They will allow us to see the use of the chain rule readily. After these instructions, stop the video in order to look at your answers. On page 49, problem 1 has 9 equations. Each equation involves the sine function, and you are to take the derivative of those expressions. First thing you should do is determine which rule you should use in order to take the derivative. And then after that, actually take the derivative of the functions, finding dy dx. If any of your forms were wrong, they will be explained as we go through the problems. A is easy. We simply take the derivative of 2 sine x and get 2 cosine x. B reads y equals sine of 2x. Best thing to do here is to rewrite that expression with the parentheses around the 2x. So the derivative of the sine of an expression is the cosine of the expression times the derivative of the expression. This is the chain rule. So y prime is equal to cosine of 2x times 2, or 2 cosine 2x. C reads y equals 2 sine of 2x. That's the same problem that we just did, but with a coefficient of 2. So our answer is 4 cosine of 2x. D is a power rule. The reason is that we write the expression sine squared of x as quantity sine of x squared. This is clearly a power rule. So the derivative is simply 2 sine x times the derivative of sine x, which is cosine x. E reads y equals sine squared of 2x. This is where things start to get a little tricky. The best way of doing this is writing this with parentheses and brackets. So y is equal to the expression sine of 2x, quantity squared. This is clearly a power rule. So to take the derivative, the 2 comes in front. We write the expression sine of 2x, and then have to take the derivative of sine of 2x, which we did in part B. That is cosine of 2x times the derivative of 2x, which is 2. The final answer is y prime equals 4 sine of 2x cosine of 2x. F reads y equals the sine of the square root of x. This is a trig problem. It's the sine of x to the 1/2. The derivative of sine of x to the 1/2 is cosine of x to the 1/2 times the derivative of x to the 1/2, which is 1 over 2x to the 1/2. Final answer is cosine of the square root of x over 2 square root of x. G, y equals the square root of sine of x, looks similar to f, y equals the sine of the square root of x, but it is a completely different problem. We write it as y is equal to sine of x to the 1/2 power. That's a power rule problem. So to take the derivative, the 1/2 comes in front. We write the expression to the negative 1/2 and then have to take the derivative of the sine of x, which is cosine of x. So the final answer is the derivative is cosine of x over 2 square root sine x. H is similar to G in that we write the expression as y is equal to the expression sine of 2x, that expression to the 1/2 power. That makes it a power rule problem. So the 1/2 comes in front, we write the expression to the negative 1/2 and then have to take the derivative of that expression. The derivative of sine of 2x, as we saw above, is cosine of 2x times 2. The 2's cancel, and our final answer is cosine of 2x over the square root of the sine of 2x. Problem I shows how complicated these can get. The problem reads y is equal to sine of cosine of x squared. We rewrite that with brackets and parentheses as shown. This is a trig problem. You're asked to take the derivative of a sine of an expression. The derivative of the sine of an expression is a cosine of that expression times the derivative of that expression. The derivative of cosine of x squared is negative sine of x squared times the derivative of x squared, which is 2x. So putting it all together, our derivative is negative 2x cosine of cosine of x squared times the sine of x squared. For problems 2 through 14, follow the same procedure. First, look at the equations and decide on the form for each derivative problem. Then stop the video and check your answers. If your answers did not match my answers, they will be explained as we go through the derivative process for each equation. Number 2 is a simple product rule. Sine times the derivative of cosine, which is negative sine, plus cosine times the derivative of sine, which is cosine. So we get cosine squared x minus sine squared x. 3 is also a product rule. So it is t times the derivative of cosine, which is negative sine, plus cosine of t times 1. Answer is cosine t minus t sine t. Number 4 involves 2 trig problems, also using the chain rule. So the derivative of sine of 4x is cosine of 4x times 4, and the derivative of cosine of x over 4 is negative sine of x over 4 times 1/4. 4 cosine 4x minus 1/4 sine x over 4. Number 5, y equals 6 cosine of x squared. The first step is the rewrite, y equals 6 cosine of parentheses x squared. And to take the derivative, we get 6 times the derivative of cosine is negative sine of x squared times 2x. Final answer is y prime equals negative 12x sine of x squared. Number 6, y equals 6 cosine squared of x. The first step is the rewrite. Y equals 6 times cosine of x, quantity squared. This is a power rule problem, so the 2 comes in front and we get 12 cosine of x times negative sine x, and the final answer is negative 12 sine x cosine x. Number 7, f of x is equal to the tangent of the square root of x. And we can rewrite that as the tangent of x to the 1/2. This is a trig problem, so we get f prime is equal to secant squared of x to the 1/2 times the derivative of x to the 1/2, which is 1 over 2 x to the 1/2. So the final answer is f prime is equal to secant squared of the square root of x over 2 square root of x. Number 8, y equals secant of x squared. First step is the rewrite, secant quantity x squared. And the derivative of secant is secant tangent, so we get secant of x squared, tangent of x squared, derivative of x squared, which is 2x. Final answer, 2x, secant of x squared, tangent of x squared. Number 9 is a little bit tricky. Y is equal to sine of quantity pi x, quantity to the 4th. This is a trig problem, and the derivative of sine of an expression is cosine of the expression, derivative of the expression. So we get cosine of quantity pi x to the 4th times 4 times the quantity pi x, quantity to the 3rd, times the derivative of pi x, which is pi. Putting it all together, we have a 4. We have a pi cubed and a pi, that gives us a pi to the 4th. We have an x cubed, and finally a cosine of quantity pi x, quantity to the 4th. Number 10, y is equal to 3 cosecant squared of x. We can write that as y is equal to 3 cosecant of x, quantity squared. This is a power rule problem. So we get 6 cosecant of x times the derivative of cosecant of x, which is negative cosecant x cotangent of x. Final answer is negative 6 cosecant squared of x cotangent of x. I'll leave problems 11 through 14 to you. So turn off the video, and for each of the problems take the derivative and then check the video to see whether you are correct or not. Number 11 reads f of x equals secant square root of 5x. The first step is the rewrite, writing the expression with quantity 5x to the 1/2 power. The derivative of secant is secant tangent. So we get as a derivative secant of quantity 5x to the 1/2, tangent quantity 5x to the 1/2, times the derivative of quantity 5x to the 1/2. That becomes 1/2 times quantity 5x to the negative 1/2 times the derivative of 5x, which is 5. And that turns out to be 5 over 2 times quantity 5x, quantity to the 1/2 power. So the final answer is 5 secant of the square root of 5x, tangent of the square root of 5x, over 2 square root of 5x. Number 12 reads f of x equals 4 secant of 3x, tangent 3x. First step is to rewrite with parentheses. To take the derivative, we'll take the 4 to the outside and then use the product rule. So we get secant of 3x times the derivative of the tangent function, which is secant squared of 3x, times 3, plus the tangent of 3x times the derivative of secant, which is secant of 3x, tangent of 3x, times 3. Since both terms have a 3, we could factor it out. We could also factor out a secant 3x. So we get 12 secant of 3x times the quantity, secant squared of 3x, plus tangent squared of 3x. In number 13, y equals the square root of cosine of x squared. The rewrite is really helpful. We write it as y is equal to the expression cosine of x squared raised to the 1/2 power. This is a power rule problem. So the 1/2 comes out front. We take the expression, write it to the negative 1/2, and then take the derivative of that expression. The derivative of cosine is negative sine of x squared times the derivative of x squared, which is 2x. Putting it all together, we get negative x sine of x squared over the square root of cosine x squared. After those tough problems, 14 may seem easy. We have y is equal to 1 plus sine of x all over cosine of x. And you can think of this as a quotient rule. So we square the bottom, and we end up getting, in the numerator, cosine x times the derivative of 1 plus sine x, which is cosine of x, minus the top, 1 plus sine of x times the derivative of cosine of x, which is negative sine of x. That gives us cosine squared of x plus sine sine squared of x over cosine squared of x. And since sine squared plus cosine squared equals 1, our derivative is 1 plus sine of x over cosine squared of x. You could also think of this as splitting it into two separate fractions. We get 1 over cosine x plus sine x over cosine x, which is secant of x plus tangent of x. Taking the derivative, we get secant x tangent of x plus the derivative of tangent x, which is secant squared x. The answers don't look the same, but they are equivalent. If you change the secant and tangent into sines and cosines, you will get the same expression. In 15 and 16, we are asked to find the equation of the tangent line at the given x value. We do this the way we proceeded before. We take the derivative and then plug in the x value. We then use the point-slope formula to come up with the equation of the tangent line. It is up to you whether you want to use the calculator as a verification. Number 15 reads f of x equals negative 2 tangent squared of 2x at x equals pi over 8. In taking the derivative, I'm skipping some steps because of time consideration. But this is a power rule. And we get negative 4 tangent of 2x times the derivative of tangent of 2x, which is tangent of 2x, secant squared of 2x times 2. At this point, we can plug the pi over 8 in, and we get negative 8 tangent of pi over 4 quantity squared, secant squared of pi over 4, and all of that turns out to be negative 16. You also have to calculate f of pi over 8. And when you plug pi over 8 into the f expression, you get negative 2. So our tangent line is y plus 2 equals negative 16 quantity x minus pi over 8. I strongly suggest you do this on your calculator by graphing the function, graphing the tangent line, and showing that the tangent line is indeed tangent at x equals pi over 8. In number 16, we have f of x equals x over sine of 3x at x is equal to pi over 2. So the derivative uses the quotient rule. We square the bottom, and then we get sine of 3x times 1 minus x times the derivative of sine of 3x, which is cosine of 3x times 3. At this point, we can plug the pi over 2 in, and we get negative 1 minus 3 pi over 2 times 0 over 1 squared, which is negative 1. We also have to calculate f of pi over 2, which is pi over 2 over sine of 3 pi over 2, which is negative pi over 2. So our tangent line is y plus pi over 2 equals negative 1 times the quantity x minus pi over 2. And that just becomes y is equal to negative x. Again, it is a good thing to verify this on the calculator. In problems 17 and 18, you are given functions and you're asked to find the 20th derivative of that function. There is no way that you're going to take 20 derivatives. So what you need to do is take the first derivative, second derivative, third derivative, etc., and hopefully you will establish a pattern making it easy to determine the 20th derivative. In 17, we're given f of x equals sine of 2x. Our first derivative is cosine of 2x times 2, which is 2 cosine of 2x. Our second derivative is 2 times the derivative of cosine of 2x, which is negative sine of 2x, times 2, which is negative 4 sine of 2x. Our third derivative is negative 4 times the derivative of sine of 2x, which is cosine of 2x times 2, which is negative 8 cosine of 2x. Finally, our fourth derivative is negative 8 times the derivative of cosine of 2x, which is negative sine of 2x times 2, which is 16 sine of 2x. It should be clear what's happening here. Every even derivative involves sine of 2x, and our coefficients are simply powers of 2. So the 20th derivative of f at x is 2 to the 20th sine of 2x. In number 18, we have f of x equals x sine of x. First derivative is x cosine of x plus sine of x. Second derivative, negative x sine of x plus 2 cosine of x. Third derivative, negative x cosine of x minus 3 sine of x. And fourth derivative, x sine of x minus 4 cosine of x. That should be enough to establish the pattern. Every fourth derivative, we get back to x sine of x. And the second term has a negative cosine x, and the coefficient is simply the derivative number. So the 20th derivative of f at x is x sine of x minus 20 cosine x.